Log on, tune in, find out. Another good idea from Cambridge.
First of 4 2-hour sessions by this work on the Langlands conjecture. We will have a short break of about 15 minutes between these 2 hours to give you a chance to have a coffee. There's also a coffee break there to have and catch up. So this will almost be at the same time, Tuesdays 10 to 12. Let me also remind you of a special lecture by Prof next Monday at 5 o'clock, and also a special program on the Langlands, Art on the Langlands program next Wednesday, a whole day program. That's also on the website. It's a great pleasure to welcome Professor Lafforgue to the He'll start his first lecture today, trying to construct explicitly kernels for Langlands functoriality.
Okay, so thank you very much. So it is very impressive for me to be here and in this magnificent lecture room. I want to talk about Langlands functoriality principle. So I was told that not everybody here knows what it is all about. So first, my lecture today will be to explain what is Langlands functoriality principle. And in the next weeks, I shall try to give new material about this subject. But first, I want to give a plan for this lecture and the next lecture. So today, I want to talk about Langlands functoriality principle. So this is classical material. Next week, I want to talk about what I call kernels for Langlands functoriality. So first I shall define what I mean by a kernel. And secondly, I shall explain that these kernels should consist in several terms. And I shall construct the main term, what I call the main terms, the main term for these kernels. The purpose of the remaining part of the lectures will be to try to construct the complementarity, the extra terms. And in order to do that, we need to talk. We shall need to talk first about Fourier coefficients of Eisenstein series. And to talk about the so-called Shalaika inversion formula. So this is this formula is classical, but I shall generalize it. So this is a formula revisited. On the last lecture in 3 weeks, will be about extra terms needed to construct functoriality kernels. So once again, the material today will be purely classical. And in the next lecture, it will be partly classical and partly new. Then I want to give at once the plan for today's talk. So first, remind a few facts about reductive algebraic groups and root systems. But here, I suppose everybody here already knows the theory. So, so this will be fast. Then I shall introduce Langlands dual group. Then I shall introduce the so-called spherical Ecke algebras and the Satake isomorphism, which is a very simple but remarkable statement, which is the basis for the whole theory. Then I shall give another formulation, an alternative formulation of Satake isomorphism using Langlands dual group. And this will allow us to define automorphic representations and to the statement of Langlands functoriality principle. So sometimes I don't say functoriality, I say transfer. So when I say transfer, automorphic transfer, it means the same thing as functoriality. Okay, so this is the plan for today's talk. So, so first I want to, if only to fix the notations about reductive groups. So it is written there. So we will be interested in, so this is a reductive algebraic group over, so first over a field K, which is separately closed. So at this point, no rationality questions, but later we will need to talk about rationality questions. So then we can choose in G a Borel pair, which consists in a maximal torus and a Borel subgroup. Of course, all Borel pairs are conjugated one to the other. So xt will be the lattice of characters from this maximal torus to the multiplicative group, and xt dual is the lattice of co-characters from the multiplicative group to the torus. And of course, these two lattices are dual, are naturally dual one to the other. Okay, so there is a pairing between these two lattices. So by now, we have the set of roots. So this is a set, a finite set, which is embedded in the lattice of characters. It consists in characters of the torus, which appear when you let T acts on the Lie algebra of G divided by the Lie algebra of T. Okay, so some non-zero characters rise in this action, and the set of characters which appear in this way is by definition the set of roots. And of course, the proper spaces all have dimension 1. Then we have the set of positive roots. So then you let T act on the Lie algebra of B divided by the Lie algebra of T. Okay, and as a matter of fact, so you have that phi T is a disjunct union of phi B on minus phi B. Okay, so by now we have the set of simple roots. So it is embedded in phi B, and it consists in roots which cannot be written as a sum of two positive roots. And any element in phi B can be written as a sum of elements in delta B. So these are simple roots. Okay. By now we have the Weil group, so sigma T, which is a quotient of the normalizer of T in G by the centralizer of T in G, which in fact is yeah, so here I should have said that this is of course we shall always consider connected reductive groups. So the centralizer is of T is T itself. So this is a finite group, and it acts on characters, on co-characters. It respects the pairing, and it preserves roots. Of course, it does not preserve positive roots. Okay. So by now you consider a root. So this is an element of phi T. Okay, so the so I don't have time to remind how is defined the associated co-root, which is an element in the dual, the lattice of co-characters. So this is a co-character which is associated to our root. And of course, the set of co-roots associated to these roots is denoted in this way. And there is also an element. So to such a root alpha, there is a naturally associated element of the Weil group. So, so here I suppose you know this, and I only recall, so this will be lemma 1, that this element of the Weil group acting on characters acts in the following way. Okay, and if you let act on co-characters, it acts in the following way. Okay, and I should also say that here the pairing of alpha, of the root alpha and its associated co-root is equal to true. Okay, So this means that alpha is sent to minus alpha, and alpha CH is sent to minus alpha CH. Okay, so you so this means that sigma alpha is an involution, and you have the basic fact that the Weil group is generated by these elements sigma alpha. Okay, so by now, if you consider two Borel pairs, T1 B1 and T2 B2, then the second one, for instance, can be written as a conjugate of the first one by some element. So G is some element of the group. Okay, you can choose an element G which verifies this property. And when you have such an element, then you have induced isomorphism from xt1 to xt2, x CH T1 to x CH T2, and so on. The same for the set of roots, the set of co-roots, for simple roots, for the Weil group. And here there is the basic fact that the isomorphism which are defined in this way do not depend on the element G. Okay? So this means that in fact all these things which so far were associated to the choice of maximal torus on the Borel subgroup, in fact are associated in an intrinsic way to the group itself. Okay, so we can change the notations and note xj, xj CH, phi j CH. Okay, but even the positive roots and the positive co-roots, the simple roots and the simple co-roots, all these things are defined in an intrinsic way from your group. Okay? So this family of xj, phi j, xj CH, phi j CH is so I don't know the English word I think is root system. So in French it is données radicielles, but the translation I think is root system or root datum. Root datum. Okay, so it is a root datum. Okay, so if you maybe it is a theorem 2. Okay, this is a root datum. So it means that we have there is a natural isomorphism from phi g to phi g CH, verifying the following things. So first, the pairings are always equal to 2. Secondly, the associated involutions, so defined by this formula so this acting on xt and xt dual, so they stabilize phi and phi CH. And the third axiom is the fact that this root datum is reduced, okay, which is the fact that for any root alpha, the only elements of phi which are proportional to alpha are alpha itself and its opposite. Okay, so when this property is verified, you say the root datum is reduced. In fact, in general, it may not be verified, and in fact, here, in some cases, you can appear the number 2. But okay. So the theorem is that if you start with a reduced connected algebraic group, then the associated root datum verifies this property. This is the first part of the theorem. The second part is the fact that if you start with any reduced root datum, there is an associated if you start with a reduced root datum, there is an associated group G, which is reductive and connected on the separately closed field K. And yes, we have a third property which in fact is important for what I want to tell after that, which is the fact that if you start with such a connected reductive group, then you have an associated natural map from the automorphism group of G to the automorphism group of the root datum. Okay, so this is the first part of the statement, and the second part is that this morphism is surjective, and the kernel of this morphism is the group of inner automorphism. Okay, and in fact, this will be important for us. Okay, so here I at once give another statement, which comes immediately after the theorem. So first so here once again I need a translation. What is the English word for épinglage? Or maybe there is no the standard translation is épinglage or. No, so I give a definition. So, and after the definition, maybe you will be able to tell me. So, once again, we consider such a connected reductive group over our separately closed Ks, and so an épinglage. So this is the Bourbaki of G. Consists in a triple. So this is a maximal torus. This is a Borel subgroup containing this maximal torus. And here we have a set of elements. Okay. So each for any simple root delta for any simple root alpha, U alpha is a non-zero vector in the Lie algebra of B, such that the torus T acts on this non-zero vector by the character alpha. So this is a proper vector. Okay, so by now, maybe you can. What is the English word? Or how do you spell it?
P-I-N-N-I-N-G.
Okay. P-I-N-N.
I-N-G.
I-N-G. Okay, so a pinning. Okay, and so here I have a definition, but so the proposition is that first any two pinnings are transformed one into the other by a unique conjugation, a unique inner automorphism. Okay? So it is important. So you see there are two assertions. First, there is always an inner automorphism which transforms a pinning into another. And secondly, it is unique. Okay? And the second statement is that any pinning defines a splitting of this exact sequence of okay. Okay. So by now, I want to say a few words about rationality questions. So by now, we are considering a group G over a field K, which is not necessarily separately closed. And so this is a separate closure of K. So if you start with such a group, of course, you can associate to it the same group over Ks, over the separate closure, and you can apply what we have said to this group. Of course, we have the Galois group of K, which is by definition the automorphism group of the separate closure over K. And here, let's consider a Borel pair, okay, in the group G over Ks. So you know it always exists. Of course, it does not necessarily exist over K. Okay. If it does exist over K, the group is called quasi-split. But in general, it does not exist over K, and you can, but you can choose such a Borel pair in GKS, and you can consider an element of the Galois group, okay, and you can consider the transform of this Borel pair by this element. So it is another Borel pair. And of course, we just said that when we have two Borel pairs in a reductive group, there is an associated isomorphism, canonical isomorphism, between the group of characters. Okay? And the same for co-characters, and the same for roots, co-roots, and so on. Okay? And so there is a so let's say things in the following way. If you have an element of the Galois group, there is an associated morphism, a morphism associated to gamma from xt to x gamma t, and so on. Okay, but by now we said before that these things can be identified in a natural way by conjugation as a unique lattice which is xj, and the same for roots, for co-roots. So this means that this element gamma defines an automorphism of this lattice. Okay? And in this way, we have an associated map from the Galois group to the automorphism group of GKS, yes, phi GKS, and so on. Okay? And so this homomorphism, this map is a group homomorphism, as it can be verified. It is continuous, which means that the kernel of this morphism is an open subgroup of gamma k with a finite index. So here we say that two algebraic groups, G and G prime over K, are inner forms, one of the other. So G primes are inner forms. When you can choose an isomorphism F between the groups over Ks defined by G and G primes, such that the composed morphism, such that for any element gamma of the Galois group, the composed of F minus 1 and the transform of F by gamma is an inner automorphism of the group. Okay? So it implies, in particular, that this morphism transforms the natural action of gamma k on this, for this which is defined by J, into the natural action of gamma k on this, which is defined by G prime. Okay? So in other words, two groups are inner forms one of the other, when at the level of Galois groups there is a twist consisting in inner automorphism. So here there is this important definition, which is if you consider such a group over K, it is called quasi-split if there is a pinning B, T, on the U alpha, which is defined not only over Ks, but over K. Okay? Of course, this does not mean that these vectors are defined individually over K. But the family U alpha, alpha in describing delta G, has to be defined globally. Of course, if the action of the Galois group on the root system is non-trivial, okay, the action of the Galois group of triple roots is non-trivial. So you cannot fix each vector individually. But what I want is the Galois group to exchange these vectors. Is that clear? Okay, so this has to be fixed by the Galois group. This has to be fixed by the Galois group, and this has to be fixed globally by the Galois group. Okay? So this is a definition of split, of quasi-split, and it is split if furthermore the torus G is a power of Gm over K. Oh, yes, T. The torus, the maximal torus T is a power of Gm over K. Okay, so here we have to know the following. So this is corollary 4. Any reductive group G over K has a unique inner form which is quasi-split. And when I say unique, it means unique up to K to some K isomorphism which preserves the pinnings. The second part of the corollary is the fact that if you consider a root system together with an action of the Galois group, okay, then this defines a unique quasi-split reductive group G. Okay, so to define a quasi-split, to define a group over a separately closed field is the same thing as to consider a root system. And to define a quasi-split group over a field K is the same thing as to consider a root system together with an action of the Galois group. This is gamma K, yes. And of course, when you consider this quasi-split group, it is split if and only if the action of the Galois group on the root system is trivial. Okay, so this is everything I wanted to recall about the general theory of reductive groups. So by now, I want to define the Langlands dual group. So this is paragraph 2. So the definition is incredibly, is very simple. So this, of course, Langlands dual we will be interested in an arithmetic situation. So this means something over a number field. So far, this theory was over an arbitrary field. But so far, we will be, from now on, we will be interested in arithmetic things, which means things which are defined on a number field or over a function field. So it will be a little easier for me to talk about function fields, but almost everything I say will be true, is true, in fact, also over number fields. But I prefer to talk about function fields because I don't have to talk about Archimedean places. Okay, so so this means that from now on, F will be a function field. So what is a function field? It is, by definition, the field of rational functions on a curve X, an algebraic curve defined over a finite field. Okay, so this is a definition. But okay, and so by now we consider a connected reductive group over F, and of course we have the separable closure Fs of S, and we have the Galois group of F, which is the automorphism group of this closure over F. So here there is a very important remark, which maybe I should have made earlier, and of course you know this remark. It is the fact that we said that to consider an connected reductive group over a separate field is the same thing as to consider a root system. But by now, in the definition of the root system, you have a lattice, the dual lattice, a set of roots, and the set of co-roots. And here there is a very important remark, which is the fact that if you exchange the lattice of characters and the dual lattice of co-characters, and if you exchange roots and co-roots, you obtain a new root system which verifies exactly the same actions. Okay? So this means starting from G, you can associate to it xg, phi g, xj naught, phi j naught. Okay? So this is a root system associated to G, seen as a group over Fs. But by now, I can exchange characters and co-characters roots and co-roots. Okay? And it is a fact that, of course, this verifies the axioms of a root system, but this also, as a consequence, this also verifies the axioms of a root system. So this is a root system. Okay? And you know that when you have a root system, you can associate to it a unique split algebraic group over any field. Okay, so this is the definition of the dual group Langlands dual group G hat. So by definition is associated to the root system xj chech, phi j chech, xj phi j. But here, of course, when I say that, I have to specify on which field. I have to choose a field. Okay? And here, it is very important to say that the Langlands dual group over C. Okay? So we started with a group over a function field, or it would be the same over a number field. But the Langlands dual group, by definition, is a group over C, over the complex numbers, okay, defined by this root system. Okay. Of course, this group over C can be, how do you say in English? You can add as an extra datum a pinning. It is endowed with a pinning. Anyway, this group is a split, so it is endowed with a pinning. So T hat, B hat, and U alpha with alpha okay. And lastly, of course, there is another datum which we forgot so far, which is the fact that we started from a group over F, but this group is not necessarily split. So the associated root datum is endowed with an action of the Galois group, which may be non-trivial. And in general, it is non-trivial. Okay? So if you exchange roots and co-roots, of course, you also have an action of the Galois group here. Okay? But here we have constituted the associated group, the group associated to the root datum, which is a split group over the complex numbers, together with the pinning. And a few minutes earlier, we said that a pinning defines a splitting of the exact sequence, which goes with the inner automorphism of the group, automorphism of the group, and automorphism of the associated root system. So this means that the action of gamma f of the Galois group on the associated root system can be lifted to an action of the Galois group on G hat itself, to endowed with the pinning, to an action which preserves the pinning. Okay? So it is endowed with a pinning and with an action of the Galois group of F. And this action preserves the pinning. Okay? This is uniquely defined up to a unique automorphism which preserves all this data. Okay, so I suppose you know examples of so the basic examples of dual groups of groups. So if you start from GLR, the dual group of GLR is GLR. But of course, I wouldn't say it is not itself, because here we have GLR over F, and there we have GLR over C. Okay? The dual group of PGLR is SLR. The dual group of SLR is PGLR. The dual group of SO2R is SO2R. The dual group of SO2R plus 1 is SP2R. And the dual group of SP2R is SO2R plus 1. Okay, so these are the basic examples. No, you don't. This is a good question. If you consider two groups, G and G prime, which are inner forms, one from the other, then the associated dual group is the same. Okay, because it only takes into account the action of the Galois group on the associated root system. And in fact, this remark is important because it will give some cases, some of the first cases of Langlands functoriality principle. Yes, so another, maybe here I have to give another family of examples, which is defined by the so-called Weil restriction of scalars. Okay, so we have f, our function field f, and we consider an extension E of f, which is finite and separable. Okay. And we also consider a connected reductive group H over E, over the big field. Then we can associate to H another group, G, which is a group over F. So you see, you go from E to F, which is called the group associated to H by Weil restriction of scalars from E to F. So the simplest way to define this group over F is to make make precise what are its points. So let's consider an arbitrary F algebra. Okay, and I want to know what is G of A. If I know, of course, G of A has to be a group, and if you know this for any F algebra, then you know the group G together with all its structures, with its algebraic structure. And so by definition, this is H of the tensor product of A with E over F. So you see, we started with, of course, a commutative algebra over F. We take the tensor product with E over F, so we get an algebra over E. And so it has a meaning to consider the group of points of H with values in this algebra. And so by definition, this is G of A. And so here there is a theorem, which is the fact that this defines an algebraic group. And if H is connected and reductive, this is connected and reductive. So for in particular, you have the following things. You have that G of F, which of course is important, is H of E. Okay? So for another, the first example is when you take H equals GL1. Okay? So this means G of H of E is E cross, non-zero elements. Okay? And so this means what you are doing, you have a torus, the torus of non-zero elements of E, and you look at it as an algebraic group over F. Of course, the rank of the group has been multiplied by the degree of the extension. Okay? So in that case, you can ask what is associated dual group of G. So in fact, it is easy to check that it is a product of the dual group associated to HI, where, so this is not I, this is iota, where iota is an arbitrary element of the set of embeddings of E in the separable closure of F. Of course, there are as many elements, the number of these elements is the degree of E over F. Okay? And so what is HI? H iota. It is H seen as a group over Fs through the embedding of E in Fs. Okay, H is a group. H is a group over E. So for each such embedding, you can see it induces a group over Fs thanks to this embedding. Okay, so this means that these Hi are not exactly the same. Okay, these H iota are not exactly the same. But there is a natural, in fact, a natural action of the Galois group on this product. So think about the most basic example. You start with GL1. Okay, so here all these things are C-cross, and the action of the Galois group is simply given by the action of the Galois group on this set of embeddings. And so this means that on this product, it acts by permutation of the coordinates. Okay. So these are the basic examples of dual groups. So by now, I have to give another definition, which so far we define this dual group, which is a connected reductive group associated to G, and it is given with an action of the Galois group. Okay, so here there is an extra definition, which is a so-called L group associated to G. So L, there are two reasons for L. The first reason is the fact that these groups allow to define L functions associated to automorphic representations, which means generalization of the zeta function. We shall see that much later. But the other reason is that L is for Langlands. So, okay, so what is it? It is denoted in this way, GL, and the L is above and just before the letter. So it is a semi-direct product of G hat with the Galois group. Okay, so this means, of course, this group is not connected. Its connected component is G hat. So it has a continuous part and a discrete part, or which is the Galois group itself. Okay, and of course, in order to define this object, you take into account the action of the Galois group on G hat. Okay, here, of course, we are in an arithmetic situation. So we have this function field f, but of course it could as well be a number field. And then we have this associated Galois group. But this Galois group has natural quotients. For instance, the quotients, which is the automorphism group of the maximal extension of f, which is everywhere unramified. So this means non-ramified. So this means you are considering the extensions which are unramified over all places. Or if S is a finite set of places, you can also consider the quotient of gamma f. So this quotient is bigger than this one. This is the automorphism group of the maximal extension of f, which is unramified at all places except possibly over S. Okay, so you allow ramification over f, and you don't allow ramification outside S. So in fact, when you consider an algebraic group over f, in some sense, which I shall make precise later, this group will always be unramified at all places except a finite number. And this implies, in particular, that the action of the Galois group on the associated root system factors through such a quotient. Okay? It cannot be, it is ramified only at a finite number of places. And because of that, sometimes we only consider we give an alternative definition, a different definition of the L group, which will be you simply take this, or with everywhere unramified Galois group. Okay. So when the action of the Galois group is unramified outside S, or when it is unramified everywhere, then you can define the L group in this way. So these are alternative yes, so we will have a break, but just before I want to define, just to give a definition. So I consider this algebraic group G over F, and I am saying that such a group is unramified at a place X. So the set of places of F is, I will denote it in this way. Okay, does everybody know what is a place? I suppose so, but this is basic arithmetic theory. Okay. So what does it mean? Unramified at a place X over F means the following. It means that if you consider G as a group over the local field F, which is deduced from F by completion at the place X. Okay, so you want this group to be quasi-split. Okay, so this means it has a pinning defined over Fx, and you want the action the action of the Galois group of Fx on the root system. You want this action to factorize through the non-ramified Galois group of Fx, which of course is the completion of Z hat. Okay, so you only have an action of the Frobenius element. Okay, so this is the definition, and as a matter of fact, for any algebraic group over our global field F, it is unramified at all places except a finite number. So you call S the set of places where it is ramified, and then you can define the L group in this way. Okay. So we have a break for 15 minutes. Now I want to come to paragraph 3, so the so-called Ecke algebras, spherical Ecke algebras, and s'attaquer à isomorphism. So in this paragraph, exactly as in the previous one, we consider connected reductive group G over our global field F, and we choose a place of F. So if F was a number field, you would choose here a non-Archimedean place. And in fact, in this paragraph and in the next one, we will be interested only in the localization of our reductive group, which means G of Fx seen as a connected reductive group over the local field F deduced from F by completion according to the place X. Okay, so we will be, so for this, once again, so after that, of course, when I will phrase Langlands functoriality principle, we will have to move again to the global situation. But first, we have to do some preparation work over which is purely local. Okay, So you consider the group G of fx, which of course is the same thing as G of fx. So, this is a group of points, and this group is a topological group. And as a topological group, it is locally compact and totally discontinuous. So this means that you can choose as a family of fundamental neighborhoods of the unit element a family of subgroups which are both open and compact. Okay? So as this group is locally compact, you can consider on this group some R measures. Okay, and in fact, this as G is reductive, this group G of fx is unimodular, which means that for R measure to be left invariant is equivalent to be right invariant. So let's choose one R measure, dgx. Of course, it is well defined up to multiplication by a scalar. There is only a choice of normalization. And then the so-called IHES local algebra associated to this group is by definition the function on the algebra of functions on this local group with compact support and which are locally constant. Okay, so which means compact support, you understand what it means, and locally constant. So each point admits a neighborhood where it is constant. Or in other terms, this function is left or right invariant by a small enough open subgroup. Okay, so this is a space, and you can define on it an algebra structure which is defined by convolution. Okay, convolution according to the R measure you have chosen. Okay, so this means that if you have two functions, f and f prime, the product evaluated in a point G is the integral over G of fx, let's say of dg, f g, f prime of g minus 1, g naught. Okay, so this is a definition of the convolution product, and it makes this space an algebra. So this is the so-called IHES algebra. So this algebra is denoted HGX. It is associated to G and it is local at the place X. So by now, let's consider a compact open subgroup of G of fx. I said we can consider arbitrarily small such subgroups. And then in the IHES algebra, you can consider the subalgebra of functions which are left and right invariant by K. Of course, this property is respected by the convolution product. Okay, and we have that the whole IHES algebra is a filtered union of these subalgebras. Okay, we also have the fact that this algebra does not admit a unit element. The whole IHES algebra does not admit a unit element. But this subalgebra admits a unit element. Here there is a unit which is the characteristic function of k divided by the volume of k for the R measure we have chosen. Okay, so by now we are interested in representations of the group G of Fx or of the Eke algebra, the local Eke algebra at X. So such a representation is called smooth when, alors, if this is a representation of the group, the meaning of smooth is any vector of pi x is fixed by some compact open subgroup k. Of course, k varies with the element. But when this property is verified by any vector, you say the representation is smooth. And if you have considered the representation of the Eke algebra, you say it is smooth when any vector of the representation is fixed by some such unit element. For some k. So this is a definition. And in fact, it is very easy to prove that to consider a smooth representation of the group is equivalent to consider a smooth representation of the Eke algebra. So far, we will only talk about smooth representations. Okay? So far, all representations considered will be smooth. So for such a representation, pi x, so by now, as they are smooth, you can consider them arbitrarily as representation of the group or representations of the Eke algebra. And depending on the context, I will use either the first point of view or the second one. Okay? By now, if you consider such a smooth representation, this representation, you can do the following. You consider such a representation on an open compact subgroup, and then you can consider the subvector space, which is the subspace of vectors which are fixed by k, or which is fixed by this element. It is equivalent. For any k, you can do that. You consider vectors which are fixed by the action of k. This is a subvector space of the whole space of your representation. And you say this representation is admissible if for any k, this subspace is finite dimensional. Okay? So in general, we will most representations we will consider will be admissible representations. And in fact, later we will consider automorphic representations. These automorphic representations have local factors, which are admissible smooth representations. So I just said it, all of them, the local factors of automorphic representations are admissible. Here there is a remark which is important, which is the fact that if you consider for such a pi x the subspace of vectors fixed by k, then this subspace is endowed with an action of the subalgebra, of the sub-Eke algebra consisting of functions left and right invariant by k. This is why, in fact, this is why in this context, the point of view of Eke algebra is better than the point of view of the group. Okay? So on this representation, there is no natural action of a group. But there is a natural action of this algebra. Okay? On Weiner, there is another remark, which is the fact that for such a pi x, so admissible, and suppose it is irreducible. And suppose you have chosen a k such that pi x of k is non-zero. Then you consider this endowed with the action of this Eke algebra, and you have that this finite dimensional vector space endowed with this action is an irreducible representation of this sub-Eke algebra. As soon as pi x is irreducible as a representation of the group or of the Eke algebra, it is the same thing, then this subspace, of course if it is non-zero, is an irreducible representation of this algebra. And furthermore, this representation is completely determined by this one. This means that if you have two irreducible representations, pi x and pi prime x, with the same associated such representations, then they are canonically isomorphic. Okay? So all of this is not difficult to prove. Okay, so here in what I have said so far, of course, we have considered arbitrary compact open subgroups K of G of Fx. There are many of them. But we would want some canonical choice for these subgroups. We would want some groups to be more natural. So I remind you that Fx is a local field. So in this local field, of course, you have a natural ring, which is a ring of integers, Ox. So for instance, if Fx is a field of p-adic numbers, this is a ring of p-adic integers. Okay? And here, of course, we would want, for instance, suppose G is GLR. Then there is a natural compact open subgroup, which is GLR of Ox. And the same for classical groups and so on. So what you would want to do in general is to define G of Ox. But of course, so far it does not have a meaning, because G is a group over the field F. And you can go from F to its localization, but this is not defined so far. So because we would want to, in fact, we would want to define this, we need some hypothesis over the group GFX. So we suppose GFX, so from now on, we suppose GFX is unramified over Fx. So in fact, I gave the definition just at the end of the first hour. So this means that on GFX, there is a pinning okay, which is well defined over Fx. And so this is a fact that this group is quasi-split over Fx. But there is a second property, which is the fact that the action of the Galois group of Fx over the associated root datum So this action has to be unramified. So this means, in fact, it is an action not of the whole Galois group, but of the unramified Galois group, which of course is the same thing of the Galois group of so kappa x. So this is the residue field, okay, which is here we have OX, and in OX we have a maximal ideal MX, and kappa x by definition is the quotient of OX by MX. Okay, so if you think of a periodic number, so these are periodic integers. This is the ideal generated by P, and this is Z divided by PZ. Okay, the finite field with P elements. Okay, so and you know that this group, of course, is isomorphic to the completion of Z. And in this group, there is a natural element which corresponds to the element 1, which is a so-called Frobenius element. It is a topological generator of the local unramified Galois group. Okay, so in fact, you suppose, this is in the definition of unramified, that the action of the Galois group is only an action of the unramified part. So in particular, we have an action of the Frobenius element on this. But of course, this action may be non-trivial. Okay. So by now, of course, our group is quasi-split. So it is not necessarily split. So this means that this torus over the field Fx is not necessarily a split torus. Okay? So then we can consider the maximal split toruses in GFX. And there is a theorem which tells us that all these maximal split toruses are conjugated one to the other. And in fact, you can choose one of them which is contained in Tx. So we shall denote maybe Txs embedded in Tx. It is a maximal split torus contained in Tx. And all maximal split toruses in GFX are conjugated to this subtorus. Okay? So here we have the following thing. Because the group GFX is quasi-split over Fx, you have the following thing. You can consider the centralizer in GFX of Txs. Okay? So this means the maximal, the subgroup of elements which commute with all elements of Txs. And of course, this centralizer contains Tx, because Tx is commutative, it is a torus. But because our group is quasi-split, in fact, it is an equality. The centralizer of Txs in the whole group is Tx. We can also consider the normalizer, okay, which will be bigger. And by now, we can consider the quotient of the normalizer by the centralizer. So by definition, this is the local rational Weil group. Yeah, so in fact, we will. It can be proved the following. So this group, which is finite, is contained. Is naturally embedded in the while group. Okay, and it consists of elements sigma of the while group, such that maybe I don't know how to, maybe W of the while group, which are fixed by the Frobenius. Okay, the Frobenius is the element there. Or if you prefer, these are the elements of the while group which are fixed by the local unramified Galois group. This can be proved. Okay. So we have this maximal split torus, and we can consider the lattice of its characters. Okay. It can, of course, as Txs is embedded in Tx, it is a quotient. This lattice is a quotient of the whole lattice of characters of Tx. Okay? And in fact, it can be identified with the quotient of this lattice by the action of the Frobenius element. You can also what does it mean? It means the biggest quotient which trivializes the action of the Frobenius element. By now, we can also consider the dual lattice of co-characters of our maximal split torus. And of course, it is embedded in the whole lattice of co-characters of Tx. And what is it? It consists in elements which are fixed by the action of the Frobenius element. Okay. By now, we have the set of roots. It is a set of characters of Txs which appear in the action on the Lie algebra of G divided by the Lie algebra of Tx. Okay? So these are non-zero characters. But of course, here, because our split torus is in general smaller than Tx, the characters may appear with a multiplicity bigger than 1. The proper spaces may have dimension bigger than 1. What is it? What is this set? It is a quotient of phi g by the action of the Frobenius element. So this is because the centralizer of the split torus is the torus Tx itself. It is not bigger than the torus itself, Tx. So because of that, it is a quotient. So which means that each root each root induces a character of the split torus which is non-zero. Okay, so here there is a lemma. No, but before that, no, not even a lemma. Simply, I say that in fact, so we have a lattice, we have a family of roots. Okay, we have the dual lattice. Okay, and in fact, it is possible to define a family of rational co-roots so that this becomes a root system. So this is a general theorem in the theory of reductive groups. I suppose you know this theorem. So this defines a root system. And in particular, you have an associated Weil group for this root system, and it is exactly what we have written there. Okay. So by now we have a lemma, which is a lemma in algebraic geometry. So this is lemma 7, I think. So let's consider the group GFX together with the pinning TX, BX, okay? So this can be extended in a unique way as a group scheme over OX, over if you, for algebraic geometer, over the spectrum of OX. Okay, it was defined as a group over Fx, but in fact it can be extended over the integers such that the fiber over the residue field kappa x is a quasi-split reductive group with associated root system, the same one. Okay. When I say here it is quasi-split, of course, this means there is a pinning, and the pinning over the reduced fiber is nothing else than the reduction of these ones. I said that, you see, this is not only the group, but the group together with the pinning, which can be extended over the whole spectrum of OX. Okay, so this means this becomes defined over OX, this becomes defined over OX, this becomes defined over OX. The whole pinning becomes defined over OX, and you can talk about its reduction over the residue field. Okay, so this is a theorem in algebraic geometry, which in fact is not difficult to prove. Essentially, if the action of the Galois group is trivial, this theorem is completely trivial in this case. And when the action of the Galois group is non-trivial, so this means there is an action of the Frobenius element, and the action of the Frobenius element defines what algebraic geometers call a descent datum. And the descent datum allow you to define this structure. Okay, but this is, so you have this lemma, and then all these objects can be seen over OX, so you can talk about GFX of OX. And you will denote that KX, or maybe sometimes KXG. Okay, and this is a compact open subgroup of G of Fx, and it is maximal for these properties. There is no bigger compact subgroup. No compact subgroup containing this one. So you can talk about that, and you can also talk about Tx of Ox and Bx of Ox. And all these groups are compact open. And Tx of Ox is maximal in Tx of Fx. Of course, Bx of Ox is compact open in Bx of Fx, but it is not maximal. In Bx of Fx, there are no maximal subgroups. You can also consider the unipotent radical of Bx, and you can also consider this group. All of this, as soon as everything is defined over Ox, by now you have all these things, which is very pleasant. And in fact, this group, so what I have denoted Kx, has very nice properties. So in the Tits theory of buildings, it is called an hyperspatial group. So it verifies the following property. So this is Kx, so G Fx of Ox. So first, I just said it is compact, open, and maximal for these properties. The second property is the fact we have an Iwasawa decomposition. So what does it mean? It means that if you consider an arbitrary element in G of Fx, you can write it, you can always write it as a product of an element Bx and an element Kx, such that Bx is in the Borel subgroup and Kx is in our maximal compact open subgroup. There is an Iwasawa decomposition. Or of course, it can also be written mu x, nx, kx, where mu x belongs to Tx, to the torus, and nx belongs to the unipotent radical. Furthermore, of course, this decomposition is not unique, but you can say what is the intersection. The intersection of Kx and Bx of Fx is Bx of Ox. And it is the product of Tx of Ox and the unipotent radical with values in Ox. So you have all these properties. So exactly in the case of GLR of Ox, for instance. Everything is well behaved. The third property is the following. You consider Tx of Ox. So this is the intersection of Kx and Tx of Fx. So the first property. And it is the maximal compact open subgroup of Tx of Fx. It is also the intersection of the kernels of all the following homomorphism. Consider any character of Tx, an algebraic character of Tx. And of course, when you have an algebraic character of Tx, which is a morphism from Tx to Gm, there is an associated morphism from Tx of Fx to Fx cross. Okay? And you can compose it with the valuation at the place x. This goes to z. Okay, so you consider all these morphisms associated to all characters of Tx. And so our group, this group is the intersection of all these kernels. So this means it consists in elements whose valuations are always 0. And the last property is the fact that the Kx, so considered as a subgroup of Fx, contains representatives of all classes of the rational Weil group. So by definition, this is the quotient of the normalizer of the split torus by the maximal torus. Okay, so you see there is a quotient. So what we say is that this compact open subgroup contains elements of the Weil group. So this is, you see in the case of GLR, GLR of OS, of OX, of course, contains all permutation matrices. And permutation matrices give you representatives of elements of the Weil group. So this is true in general. Okay, this is the end of the lemma. Okay, so if you remember, earlier in we have chosen R measure on G of Fx, but here we had a choice. There was you needed a normalization, so we decide to normalize it in such a way that the volume of our distinguished compact open subgroup is 1. So, for instance, for GLR, you decide that GLR of OX has volume 1. This is a natural way to normalize the R measure. Okay, so by now, this is a measure on G of Fx, but you can also consider Tx of Fx, and then you consider the R measure such that the volumes of Tx of OX is 1. It is also natural. And lastly, you can consider NBX of Fx, and you consider the R measure dNx such that the volume of NBX of OX, which is compact open, once again, so these volumes has to be 1 also. Okay. So with these choices, there is a lemma which gives you an integration formula. So let's consider a function on G of Fx, which is locally constant with compact support. Okay, so an element of the Ecke algebra. And then you have the following integration formula. So with our choice of R measures, the integration over the whole of Fx can be made in 3 steps. So an integration on the torus an integration on the unipotent radical and an integration on our distinguished compact open subgroup. Of course, because of the Iwasawa decomposition, this element, this is a general form for the elements of G of fx. But here we say a little more. We say that, in fact, this gives an integration formula. Okay. So in order to phrase the Satake isomorphism, I need extra notation. So I'm sorry, but okay. So so far we have considered we considered the torus Tx, the maximal torus Tx, and inside there is this subtorus, this maximal split subtorus. Okay, and we have considered, of course, the lattice of characters. Okay, and inside I define another lattice. This is a set of characters which are fixed by the Frobenius element. Okay, so by definition, yes, so lambda x is defined is embedded in xj, but also it is embedded in xj x, but it is not necessarily equal. I remember that this is the quotient of xj by the action of the Frobenius element. So in fact, these two lattices are almost equal. This is embedded into this one, and the quotient is finite. But there may be a little difference in general. Okay, so by now there is a dual lattice. Okay, and so this means that the dual lattice of this is embedded in this dual lattice. Okay, so this is purely formal, deduced from that. By now, here there is a statement. There exists a unique homomorphism, which is denoted the maybe order homomorphism or valuative homomorphism, which goes from Tx of fx to the dual group of lambda, the dual lattice of lambda x. So how is it defined? I want the following. For any character chi of Tx, okay, so this is a character of this is an element of xt or xg, the lattice of characters, for any chi, and for any element of Tx of fx, I want the following. I want the pairing of chi and the image of mu x by this morphism. So here you see I have this is an element of the dual of lambda x. Yes, and here I want a character which is fixed by Frobenius. So this means this is an element of lambda x. So here this is an element of lambda x, and this has to be an element of the dual of lambda x. So it has a meaning to talk about the pairing. And this has to be the valuation of the image of mu x by the character. Okay, so what is this morphism? This morphism tells you that you start with an element of Tx of Fx, and when you compose it with characters fixed by Frobenius, you get elements of Fx cross, and you can consider their valuation. Okay, and so this morphism is it is exactly the nicest way to factorize together all this valuation morphism. Okay, if you prefer, lambda x dual is the natural image group for all possible valuations taken together. Okay, you see, think about the case where everything is split. Then you have gm to some power. Okay, so when you take rational coefficients, you have fx cross to some power, and when you take valuations, you have z to the same power. So this is lambda x dual. Okay, but of course, in general, there is an action of the Frobenius element, and so you need to be a little more careful. Okay, so because of the property 3 of the lemma, we have the following exact sequence. Tx of fx goes to lambda x dual, okay, through this order homomorphism. And what is the kernel? According to the lemma, it is Tx of Ox. Okay, we have such an exact sequence. If you prefer, it is another definition of lambda x dual. By definition, it is a quotient of this by that, which we already defined. So said in this way, this means we have the quotient lambda x dual defined in this way is naturally the dual of lambda x defined in this way. So here is the statement. Okay. So by now, so we have this exact sequence, and on this exact sequence, there is a natural action of the rational Galois group. So this means the action of the rational Galois group respects this exact sequence. Okay, it naturally acts of all these things. You see, these things were defined by considering fixed points under the Frobenius element. So it is because of that, of course, this group, which consists of in elements of the Weil group which are fixed by the Frobenius, this group acts on this object, and it respects the exact sequence. Okay. So by now we shall okay, so we have this lattice, and we shall denote like that the group algebra of our lattice. Okay. So what it can be identified with the convolution algebra of functions on Tx of fx which are invariant by Tx of Ox, okay, according to our exact sequence. And exactly as the lattice itself, this algebra is endowed with an action of the rational Galois group. Okay, so we have always almost all notations we need. By now, I want to introduce the so-called spherical Ecke algebra at X. So this is a local algebra. So I will denote it in this way, HJX, and here with the empty sign. So by definition, this is the algebra associated to the compact open subgroup Kx. Okay? So earlier in the talk, we defined this type of algebra for an arbitrary compact open subgroup. But when we choose this distinguished compact open subgroup, there is an associated algebra, which by definition is a spherical Ecke algebra. This is the definition of the word spherical. So it consists in functions with compact support, which are left and right invariant by this subgroup. And it has, of course, there is a unit element, which is the characteristic function of Kx. Of course, you don't need to divide by the volume, because you choose normalization in such a way that the volume is 1. Okay, so we almost have everything we need to state the Satake isomorphism. Okay, so in order, we need another last notation, which is a modular character. Rho bx, so it goes from bx of fx to qx to the power z. So qx is by definition the number of elements of the residue field kappa x at the place x. Okay? So of course, there is always an ambiguity about the modular character. So it is defined by the following formula. So you consider a function, and you want to integrate it on the unipotent radical, but you twist the integration measure by conjugation by bx. And so the modular character is the character which tells you how the R measure is transformed. Okay? Of course, any element of bx normalizes the unipotent radical. Okay, but so this means that when Ex describes this unipotent radical, this also is in the unipotent radical, but the R measure is changed, and it is changed according to the modular character. Okay, so by now there is no ambiguity, and I can state the Satake isomorphism, which is really it is in fact a simple result. It is not difficult to prove, but it has huge consequences, and it is the basis for the whole Langlands program. So this is theorem 10, Satake isomorphism. So let's consider a function which belongs to the spherical Ecke algebra. So this means this is a function on g of fx, which is left and right invariant by kx, by gfx of ox. Okay? And you associate to it something which I denote in this way. So this thing which is associated to x is a map. It is a function on Tx of fx, so I need to define what is the image of an arbitrary element. Okay, so you see this is a function of Tx of fx. And I need to define what is the image of an arbitrary element. So what you take is to integrate on the unipotent radical of fx the function hx evaluated at mu x multiplied by nx. Okay? And here you need to correct it by the square root of the modular character. Okay, so you see here what you have is almost the integration formula I gave a few minutes ago. But of course I have forgotten the kx part because I am starting with a function which is left and right invariant by kx. So we don't need to integrate along kx. So we integrate along nx and we evaluate at mu x. So we get a function, and we multiply this function by the square root of the modular character. So in this way, we get a function of t on Tx of fx, which has compact support, and which is invariant by Tx of Ox. So this means that in this way, we have defined a map to this algebra. I said that this algebra is the elements of this algebra are functions on Tx of fx, which are invariant by Tx of Ox. Okay, so we go to this algebra. So the theorem tells you that this is an algebra morphism. So this means it is compatible with products defined by convolutions. Of course, this is why we have introduced this factor. Without this factor, it would not be compatible with multiplication. So this factor is chosen so that it respects multiplication. So it is an algebra morphism. Second part of the theorem, it takes values not in the whole algebra, but in the part of the algebra consisting of functions which are invariant by the action of the rational Galois group, of the rational Weil group. And the third part of the theorem is the fact that it is an isomorphism. So so you see, for instance, in the case of think about GLR. So in the case of GLR, without action of the Galois group, this is z to the power r. So the group algebra is the algebra of polynomial functions in r variables, and this subalgebra is the algebra of symmetric polynomials in r variables, which means polynomials which remain invariant by the action of the symmetric group. But okay, so the theorem tells you that it is true for any local reductive group as soon as it is unramified. And of course, there is something, so this gives you exactly what is this algebra. So it is an algebra of invariant polynomials. You can phrase it that way. But as in particular, it has a very important property. This algebra is commutative. Because this algebra, a polynomial algebra, is commutative. Of course, the whole EQ algebra, the convolution algebra on the group G of fx is not commutative. And in general, for a compact open subgroup, the subalgebra of functions which are left and right invariant by k is not commutative. But here, part of the statement is the fact that when you have chosen k equal to kx, then the associated invariant algebra is commutative. Okay? And in particular, it has a very important consequence. It is the fact that the irreducible representations of this algebra have dimension 1. They are characters. Yeah, so today I will not go further that paragraph 3, but if you allow me, I want to finish to make a few remarks, which are consequences of what I just said. We said we are interested in representations pi x of g of fx, which are smooth. So this means it is the same thing as a representation of the whole Eke algebra. Okay? So a representation which is smooth, which is admissible. Then and of course we are particularly interested in representations which are irreducible. So by now, suppose you have such a representation such that the vector space, this vector space, is non-zero. Okay? So I said that this vector space is endowed with an action of the Eke algebra of functions which are in left and right invariant by kx, which means the spherical Eke algebra. And I told you that as soon as this representation is irreducible and this subvector space is non-zero, this subvector space is an irreducible representation, and it determines the representation pi x you started with. But suppose you are in this situation, this representation has to be irreducible. So it is an irreducible representation of a commutative algebra. So it is a character, it has dimension 1. It implies the dimension of this thing is 1. Okay? And it is the action of the algebra on this dimension 1 space is given by a character. Okay, so because of that, we say in general that such a representation pi x is unramified if this subspace has dimension 1. Okay, and so it is completely determined by a character of our algebra. Okay, so by now, this will be the end of my talk today. We can think a little about what is a character of this algebra. Or in other terms, what is a character of this algebra? How to define character of these algebras. So I remind you, this algebra, without this algebra can be identified with, it is the algebra of, this is a convolution algebra of functions on Tx of fx, which are invariant by Tx of Ox. And then you have to take the subalgebra of invariant functions. Okay, so how to define a character of this convolution algebra? So a simple way to do that is to consider a character of Tx of fx which is invariant by Tx of Ox, and which factorizes, so this means it factorizes by this, with values in C cross. Okay, so let's consider a character of Tx of Fx, which is invariant by that, invariant by Tx of Ox. Then there is an associated character of the convolution algebra of Tx of Fx divided by Tx of Ox, which is nothing else than C of lambda x dual. So how is it defined? You consider a function, and you associate to it the integral over Tx of Fx of z of mu x phi of mu x. So this means each time you have, as soon as you choose a character of Tx of Fx which is invariant of Tx of Ox, you have an associated character of this algebra. But you can prove easily that in fact all characters of this algebra have this form. Okay? And of course, when you have a character of this algebra, it induces a character of this subalgebra. And by now, and here there is a statement, which is the fact that all characters of this subalgebra are induced by such characters of Tx of Fx. And when you have two such characters of Tx of Fx, z and z prime, you can ask when they induce the same characters of this Eke algebra. And the answer is that they induce the same characters of this Eke algebra if and only if they are deduced one from the other by the action of the rational Weil group. Okay, so once again, think about GLR. So in the GLR case, what you consider is characters of Fx cross to the power R, which factorizes through the valuation. So this means characters of z to the power R. They consist in a family of R numbers. Okay? You have to decide what are the images of the vectors of a basis of z to the power R. So it consists in R vectors. So this means every time when you choose R complex numbers, which are the images of these vectors, R non-zero complex numbers, it gives you a character of the algebra of polynomials, and so a character of the algebra of invariant polynomials. And when do two such families of R non-zero complex numbers induce the same character? When these two families of R numbers are deduced one from the other by permutation, which means by an action of the Galois group, of the Weil group, which is the symmetric group, sigma R. Okay? So this means in that case, to give a character of the Eke algebra is the same thing as to give a family of R non-zero vectors, non-zero complex numbers, up to permutation. And of course, when you say that, you may think of a natural way to consider a family of R numbers up to permutation of the vectors. It is to consider these R numbers as the eigenvalues of a matrix, of an invertible matrix of GLR of C. Okay? And in fact, so this will be the subject of the next paragraph, which I shall give next week. So this will be the new interpretation of the Satake isomorphism, which was given by Langlands. And after that, we will keep on studying the theory. So I am already late, but okay. So I have spoken too much. So thank you.
Questions or comments? That's not the case.
Do I go too slowly or too fastly, or please tell me. Today I was, from my point of view, I was slow, but so I could go faster. Or what do you think? So I don't know what you know and don't know, and so
Don't
or
go
maybe
faster.
you
I
will.
just heard don't go faster. Don't go any
Don't
faster.
go any faster.
Okay, so okay.